Okay, so this is going to be the lecture video for 5.2, which is verifying trig identities. So 5.1 is where we had that nice long list of all these different trig identities, like the reciprocal identity and our Pythagorean identities and all those kinds of things. So you're definitely going to want to have those out and have those ready for this lecture and for this assignment because you're going to use them. This is kind of the lecture that I mentioned where you're going to treat it almost like you did in geometry, where you had like 2-column proofs, because they're going to give you something like this and it says verify. So we're not solving, we're not trying to figure out what theta equals. What we're trying to do is we're trying to make sure that what's on the left actually equals what's on the right. And we have to use all these different identities in order to do that. So before we actually get going on trying to do one like the one on the board behind me, here's some helpful hints for verifying trig identities. First thing is to know those fundamental ones. Those are the ones from 4.1. Those are where you know your Pythagorean and your reciprocal and all that kind of stuff. You definitely want to know those. And I told you you didn't have to memorize them, and I'll stick with that. You don't have to memorize them. But if you're having to look down that list every single time and you're not just learning them, then it takes you a lot longer to accomplish this stuff. So you're definitely going to want to use that and you're going to want to learn it. And the more you use them, the more you're going to learn. So that's going to come naturally just as you work through some of these problems. Step 2 is you're going to want to try and rewrite the more complicated side as the simpler side. So even just looking at the first example that we're going to do, we have cotangent of theta plus 1 equals the cosecant of theta times the cosine plus sine of theta. So there's a lot of stuff on this right-hand side. And so one of the ways that you can approach these is you can take the more complicated side and let's see if we can work through it using some of our identities and make it look like our easier side. So that's a helpful hint. Another hint is sometimes it's easiest to get things in terms of sine and cosine and then simplify them. We actually saw that a little bit in the 4.1 stuff on those confusing problems where it said, you know, get things in terms of sine and cosine and don't have a quotient. But at the end, we didn't usually end up with a sine or a cosine. We ended up with a secant or a cosecant or something else like that. That's another tool though to use here. Maybe instead of thinking about cosecants and cotangents, maybe we need to get these in terms of sines and cosines and start seeing if we can get something equal. Another option or another hint is that usually factor and use the algebra to simplify it. So everything from college algebra, factoring and perfect squares and all that kind of stuff, that still comes up here in trig. We're just using trigonometric functions instead of polynomials or instead of quadratics. And so here are some common algebraic identities. We have the sum of squares, we have the difference of squares, we have x to the third minus y to the third, and how that breaks apart because that's a difference of cubes. And then we have the sum of cubes and all of that kind of stuff. So those are really nice to also add to your list of identities. These are obviously, they're not trig identities, but they apply to trig identities. And so there's an example there at the bottom where sine squared of theta plus 2 sine of theta plus 1. Well, if you look at that one versus the very top where we have x squared plus 2xy plus y squared, we can automatically factor that then because it's the same format. It's the same identity. And so we can factor that into sine theta plus 1 quantity squared. And so again, this is going to be a lot like how you learn to factor. When you learn to factor, if you learned what I consider the old school method where you had to sit and think about it and you had to think about the factors of your C that added together to give you your B and all that kind of stuff. It was trial and error sometimes. You had to sit there and play around with it. And this is definitely a section and a chapter where we're going to do a lot of playing around. And you may go off down a rabbit hole and it doesn't help you at all and you have to erase it, or go off down a rabbit hole over here. And actually, I said erase, but I really strongly recommend that you don't erase if you go off somewhere and you don't end up where you thought. Like if I start trying to verify this side equals this side and I'm not getting there, don't just erase it and say, well, that was a waste of time. Because what can happen is sometimes then we'll play around with this side for a little bit and we can actually meet a middle ground. We can get somewhere else. to like a third stage is what it's going to say later. I have a star note later on after one of the problems. And so I don't want you to erase everything because you might end up using it later on. Okay, so those are all the trig identity kind of helpful hint things in your algebraic identities. Obviously, if you're still writing, you might want to pause because I'm going to move straight into verifying our first identity. We're going to use the identities to verify that cotangent of theta plus 1 equals cosecant of theta times cosine of theta plus sine theta. So obviously, this right-hand side is way more complicated. So I'm going to start with that. I'm going to work on this and try to get down to cotangent theta plus 1. That's what I'm going to do. So I'm going to write it over here where I have cosecant of theta times cosine of theta plus sine theta. Okay, that's my starting point. And my end point, what I want to get to is this cotangent of theta plus 1. So I need to think about getting some stuff moved around. And I need to get to cotangent, and so I'm not really sure how to get to cotangent with cosecants and all that kind of stuff. So what I'm going to do is I'm going to try getting everything into sine and cosines. So I know that cosecant is 1 over sine. So I'm going to replace this cosecant of theta with 1 over sine theta. And while I'm not going to write it on the board, I do want to show you that in my notes, I'm pretty happy with my notes. I think they turned out really nice. As we work through these, I kind of give you a why column and try to explain why we did this. So right here, I just simply substituted in that 1 over sine theta. So I'm not going to show you all that because I want you to follow along with me. But if you do have my notes pulled up as well, you can see exactly why. And I'll tell you why as I'm doing it, but on the paper, it's still there. Okay. So I replaced cosecant with 1 over sine. Now, I'm not sure exactly what to do, so I'm going to distribute. Let's see if that's going to help us get anywhere. If I distribute 1 over sine theta, that's going to give me cosine theta over sine theta plus sine theta over sine theta. Okay. Well, I know this is going to go to 1. That's good because that's kind of what I need. And then what about cosine theta over sine theta? What does that equal? That equals cotangent theta. And then sine over sine is 1. So right there, we're done. We verified that all of this on the right-hand side actually does equal the cotangent plus 1. And so we did kind of a 2-column proof in essence, where I just manipulated this around, replaced it with its equivalencies and the identities, and was able to prove that cotangent theta plus 1 does equal cosecant theta times cosine theta plus sine theta. And that's how these problems are going to work. And like I said, you could have approached it from a totally different direction. You could have done it a different way, and there's nothing wrong with that. It just may take you longer, or it may take you just a different route. There's definitely more than one way to get to the end of these problems. If you think about traveling and you think about even driving to Kansas City, you can drive up the Missouri route, you can drive up the Kansas route. Both routes will get you to Kansas City. So don't feel like if you see me do a specific route that is the route you have to take. I will say I took my routes based on the book, and so, I feel like mine are probably the shorter route. But that doesn't nullify any route that you may choose to take. So let's do another one, because that's what we're going to do now for the rest of this lecture, is we're going to verify different trigonometric expressions and functions. And they're going to get progressively harder. And we're going to have to use a lot more tricks. Tangent squared x times 1 plus cotangent squared x equals 1 over 1 minus sine squared x. All right, so this one's obviously a little bit harder. We got some squared trigonometric functions going on here. And while both sides are more complicated than our last problem, I would still say that this part over here on the left, the tangent squared times the 1 plus cotangent squared, I would say that's probably more complicated. So I'm going to start with that one. And since it's already on the left-hand side, I'm not going to rewrite it. So I'm going to, I guess, distribute first, because that seems a good thing to do, get rid of those parentheses. So if I distribute my tangent squared x, I get tangent squared x plus tangent squared x cotangent squared x. So all I did was distribute. And then I need to think for a moment if there's a way, because this is kind of a mess over here, the tangent squared x, cotangent squared x. But what do I know about tangent and cotangent? Well, I know that they're reciprocals of each other. I know that tangent equals 1 over cotangent. I know that. That is a reciprocal identity. I can do the same thing when it's squared. It doesn't change anything just because I have it squared. So I can think about changing the cotangent squared x into 1 over tangent squared x, because cotangent is 1 over tangent. And hopefully you see why we might want to do that, because if I have tangent squared times cotangent squared and I write it like this, then I'm going to have tangent squared over tangent squared, which is going to give me 1. And that's a lot nicer, because then I'm just going to have tangent squared x plus 1 over here, which still doesn't really look like anything like this yet, but at least it's getting somewhat simpler. It's getting somewhat nicer. And I think, if I remember correctly, from 5.1, we have a Pythagorean identity that tells me what this is. It says tangent squared x plus 1 equals what? It equals secant squared of x. You're like, okay, so that's good. Now we've condensed all of this down to secant squared x. So now we're going to need to figure out how to get secant squared x to look like 1 over 1 minus sine squared x. Well, what is secant squared x? What do we know secant is? Well, secant is 1 over cosine, right? So secant squared is 1 over cosine squared x. So we have that. And then we have additionally from the 4.1, again with our Pythagorean identities, we know that cosine squared x equals 1 minus sine squared x. This was one of our identities from 4.1. So if I put that in, I have 1 over 1 minus sine squared x. And that's where I was trying to get to over there on the right-hand side. So we used a lot of reciprocals here. And then we used a couple of our Pythagorean identities in order to manipulate things around. So sometimes when you're playing around with these, you're not actually sure where you're going to go, because like thinking you're going to make a pit stop here at secant squared, that might not make a lot of sense when I'm trying to get to sine squared. But if you keep going and you keep making those pit stops, you do actually end up getting to your final destination. Like I've said, these are ones that are going to take practice. These are ones that are weird and you just have to kind of get used to it. All right, let's try another one. And I'm going to erase the word verify just to simplify the board a little bit, because I think you understand we're going to verify all these. All right, let's see. Let's do another one. We have tangent of t minus cotangent of t all over sine of t cosine of t equals secant squared of t minus cosecant squared of t. And just so you know, personally, I hate using any other letter besides theta because I think it makes it look more complicated. But I wanted you to see it with X and with T because obviously they're going to give it to you with other letters for the test. Whenever I make a test, I'm going to always use theta because I think it keeps it nicer. But that's just a side note. Okay, so you could start with either side. I think this side looks a lot more complicated because it has a fraction. And so sometimes getting rid of that fraction is going to get us over to the other side. So I'm going to work on this side. And notice that we have two terms on top, but only one term on bottom. So since we only have that one term on bottom, what I can do is I can split it. I can split my fraction up. That doesn't mean I split the bottom, but I can split the top. I can take tangent of t, and I can put that over sine of t cosine of t minus cotangent of t over sine of t cosine of t. Basically what I did is like the reverse of the subtraction process where we put them together. Okay, so why is that helpful? Well, maybe it's not just yet. So let's pull our tops out to the side. And I'm going to take things in a lot of steps. Maybe you can take things more steps at once, but I definitely don't want to lose anybody as to what I'm doing and where I'm doing it. Cotangent of t times 1 over sine t cosine t. Okay, so all I did was I shifted things over. And the reason why I decided to do that is because I'm going to think about getting tangent and cotangent in terms of sine and cosine. And so instead of putting a fraction in a fraction, I moved it over to the side so that when I do this conversion, that I don't have fractions in a fraction. Because tangent is sine over cosine. Cosine t. And cotangent then is the reciprocal of that. So it's going to be cosine over sine. Okay. So why is that helpful? Well, because now if I look, I have a sign on top and a sign on bottom. Oops, there should be a t in there. So I could cancel those, which just leaves me with 1 over cosine squared t. And then I can do a similar process over there where I have cosine on top and cosine on bottom. So I have minus 1 over sine squared of t. Okay. Well, what is 1 over cosine? We just saw this reciprocal played out in the last one. 1 over cosine is the same thing as secant, right? So 1 over cosine squared is the same thing as secant squared. And 1 over sine is the same thing as cosecant. So 1 over cosine, or excuse me, 1 over sine squared is cosecant squared. This was exactly what we're trying to get from up here. And so this is where we really see that getting things in terms of sine and cosine a lot of times will help us to cancel things out and get us to simpler expressions to play around with that will help us get to the other side. All right, let's do another one. Remember, if at any point I've gone too fast, you can always pause the video and keep writing to get to where I'm at. All right, let's do another one. We're going to verify that cosine of x over 1 minus sine of x equals 1 plus sine of x over cosine of x. So this is what we're going to verify. So how should we do it, do you think? I think I want to look at this side. I'm going to look at that side. And what I'm going to do is I'm going to try and get kind of like a common denominator of sorts. Because really what I'm going to do is I'm going to try and move this over, almost treating it just like an algebraic expression. And like I said, there's more than one way to do this. Let me think. If I do that and that, yeah, you know what I'm going to do? I'm going to do it a little differently than I did in my notes, because I think this way makes a lot more sense. So notice for this problem, we have one fraction equals one fraction. Back in college algebra, or even a math class before that, when you have a fraction equal to a fraction, that's known as a proportion. And you can solve proportions using cross multiplication. So if we use that same concept here, I'll take cosine times cosine, which will give me cosine squared x equals, if I take this times this, then I have 1 minus sine x times 1 plus sine x. So I'm going to have to do my FOIL method. Okay, so I have cosine squared x equals, if I do first, I get 1. Outer, I get sine x. Inner, I get minus sine x. Last, I get minus sine squared x. So notice the middle terms go away, so that I get cosine squared x equals 1 minus sine squared x. This is our Pythagorean identity. And so sometimes you can work through these and you're not actually verifying the other side. Like I didn't get it to look like the other side, but what I got was a truth. I got an identity down here, which means it works. And so sometimes you're not going to necessarily be working to make it look like the other side. Sometimes you're just going to be working towards a truth or an identity itself. There's an extra note here in the notes after that problem where it says sometimes it's best to work on both sides and reach a common third side, which is kind of what we did here. When I cross multiplied, I was kind of working both the left and the right side at the same time, and I reached a common third side or a common truth, an identity that worked. And so that's another way that you can approach these. The next example, we will very much do a like a common side. Like we're going to work one side for a little bit, and then we're going to work another side and do that. So let me erase this and put the next problem up. Oh. We are going to verify secant of alpha, I think. I don't even remember which symbol that is. But it's in your book, so I want to make sure that you were exposed to all of them. And now I'm blanking on what the name of that symbol is. Give me a minute, it'll come to me. One plus two sine. Let me look for a second. It's not helpful. It is an alpha. I was right. I shouldn't second guess myself. Okay, so it's an alpha. Okay, all of that to say, if you look at this, if you look at either side of this, it's a lot of stuff. So I wouldn't say that there's necessarily an easier side than the other, like we've kind of talked about on all the rest. So what we're going to do is we're just going to play around with one side for a little bit, and we're going to try and make it nicer. And when I say make it nicer, usually what happens is we get it into terms of sine and cosine. And then once we get there, we kind of pause, and then we're going to go over to the other side and play around with it for a little bit and see if we can't get the same middle ground. Because if at some point we can get the same thing over here as over here, even though it's not the starting point, we still verify that they are equal. So I'm going to start with this side, with secant alpha plus tangent alpha all over secant alpha minus tangent alpha. I'm going to start with that side. And I'm going to say, okay, what can I do here? Well, I don't know for sure. But I do know that over here, I tried to get to cosine squared on bottom, right? So I know I need to get some cosines in there and all that kind of stuff. So I'm going to do something kind of weird, and your book does it, and so I want to make sure I include it here. I'm going to multiply the top and bottom by cosine alpha over cosine alpha. What is cosine alpha over cosine alpha? It's 1. I'm just trying to introduce some cosines. I could have done sines, but I'm not trying to get to a sine. I'm trying to get to a cosine. So I'm going to multiply both sides, or excuse me, top and bottom of this left side by cosine alpha over cosine alpha. Okay. I'm going to distribute so that I have cosine alpha secant alpha plus cosine alpha tangent alpha all over. Oops, let's do secant first, or cosine first. Cosine alpha secant alpha minus cosine alpha tangent alpha. Okay. So why would I do that? Why is this helpful? Well, what do I know about cosine and secant? I know that they are inverses of each other. I know if I take cosine times secant, I'm going to get to 1. And so that's one of the reasons why I went ahead and multiplied by cosine alpha over cosine alpha. Because by introducing these cosines, I know some of this stuff is going to simplify. All of these cosine secants are going to go to 1. And that makes it a lot nicer to work with. Because then I'm going to have 1 plus cosine alpha tangent alpha over 1 minus cosine alpha tangent alpha. Okay. Now, like I said, sometimes I don't know exactly what to do. So let's get everything in terms of sines and cosines, and then that might help. Remember, tangent is sine over cosine. So I can put 1 plus cosine alpha times, and then instead of writing tangent, I'm going to write sine over cosine. Sine alpha over cosine alpha. And then I go to the bottom and do the same thing. 1 minus cosine alpha times sine alpha over cosine alpha. Hopefully you can see that. There you go. Because then I have a cosine cosine and a cosine cosine, which leaves me with 1 plus sine alpha over 1 minus sine alpha. All right, so I got rid of all my secants and tangents, and I got everything down into the most simplified form I can think of in terms of sines and cosines and everything like that. So I'm going to leave that left-hand side alone. I didn't verify it with the right-hand side yet, but I'm going to leave it alone because I'm going to see if I can't maybe get this right-hand side to look like this. Because if I can get it to look like this, then I've verified them together. So now we're going to play around with this. With this 1 plus 2 sine alpha plus sine squared alpha all over cosine squared alpha. Well, this top one, if I scroll back up to the top of our notes, this top one looks a whole lot like our x squared plus 2xy plus y squared bit that we had. And so if that's the case, then I can factor it. I can turn it into, what would it be? 1. Let me write a plus when I say 1. 1 plus sine alpha quantity squared. All I did was use the algebraic identity right here at the beginning of our notes, which says that x squared plus 2xy plus y squared equals x plus y quantity squared. So I can do that. And then all of that is over cosine squared of alpha. Okay. So that's good. Now, there is a Pythagorean function or identity that says cosine squared of alpha that we've used a couple different times equals 1 minus sine squared of alpha. So I have 1 plus sine alpha squared all over 1 minus sine squared of alpha. Okay. Now, these are getting close, but they're not exactly the same thing. So let's think about how we would factor. Like this, if we look at the bottom, look at this. We have a 1 minus sine squared of alpha. 1 is a perfect squared. 1 times 1 is 1. Sine squared is a perfect squared, so we have a difference of squares, which again, you can see right there on my notes, is right here. This x squared minus y squared equals x minus y times x plus y. So on the top, I'm going to write that 1 plus sine theta twice. I'm going to factor it out or show it in its longer form because I have a feeling something's going to happen here. Because if this is going to factor into 1 plus sine alpha and 1 minus sine alpha, then we're going to have some stuff cancel. Because now I factored the top and the bottom, and on both the top and the bottom, I have this 1 plus sine of alpha, leaving me with 1 plus sine alpha over 1 minus sine alpha. And look, that's exactly what I got when I played around with this other side. I just verified the original expressions because I was able to get the left-hand side to 1 plus sine alpha over 1 minus sine alpha, and I could get the right-hand side to 1 plus sine alpha over 1 plus or minus cosine alpha. So sometimes you're not actually going to get over here. Now we could, like if you really wanted to keep taking it, we could have thought about like you basically move back up and then you would get to the other side. And so we're kind of doing a big loop to get around to it. But instead of doing that, because honestly, I would never think to take 1 plus sine alpha times these two different things to move back up this side. So sometimes it's easier to break down the sides to get to that third middle ground. All right, I have an extra example, and it says, I got it from page 209 in your textbook. It's number 69, so it's just one of the problems like at the end of the chapter. But I'll go ahead and work it since this is a lecture video. Obviously, we can be over the normal lecture time because you guys are watching it at your leisure at home. So here's a bonus problem. I did work it out in my notes as well, but just so you can see it. we have tangent squared theta minus 1 all over secant squared theta equals tangent theta minus cotangent theta all over tangent theta, the crack is hard to do, plus cotangent theta. Okay. So I'm going to start with this left-hand side. And the reason why I'm going to start with the left-hand side is because I pretty quickly recognize that tangent squared theta minus 1 is one of our Pythagorean identities. Or rather, the secant squared theta gives me a Pythagorean identity. The secant squared theta equals tangent squared theta plus 1. So I can replace that on bottom with a tangent squared theta plus 1. And on top, we have a difference of squares again. We have tangent squared, and then 1 is squared. So we can have a tangent theta minus 1 and a tangent theta plus 1 all over tangent squared theta plus 1. We're like, okay, so how's this helping? How are we going to do this? Well, I'm not sure. So let's play around the other side for a minute. We have tangent theta minus cotangent theta over tangent theta plus cotangent theta. Let's get them all to be tangents for a moment. If I want to make cotangent into tangent, then I write it as 1 over tangent, like that. And then I have tangent theta plus 1 over tangent theta. And we're like, well, great, we got fractions and fractions. Those are always fun. So let's get rid of those fractions and the fractions. How do we do that? You multiply the top and the bottom by tangent theta. When you multiply the top and the bottom by tangent theta, what happens is these will simplify down into 1, and we will no longer have a fraction and a fraction. So we have tangent squared theta, because we have to distribute, minus 1 over tangent squared theta plus 1. Wait a second. Does this ring a bell? Hopefully it does. Over here. We got it over here. And so I like this problem because I like to show you that sometimes you start working a side of it and it's like we got down to here and we're really sure what to do next. So then it's like, well, let's go play around on this side. Let's see what happens. And then we actually, like the very second step on the left-hand side is where we should have stopped because we got there on the right-hand side. And so that's why I strongly recommend don't erase your work as you're working. Even if you think you went down a rabbit hole and you're like, I have no idea where I'm going with this. Because what can happen is, yeah, maybe you went down a rabbit hole over here, but maybe one of those steps over here is going to be the ending point for you on the other side. So don't erase, don't quit just because on one side it looks really weird and wonky. Play around with the other side first and see if you can't also get to that same weird and wonky place, because you might be able to. And that is the end of 5.2.